Hello everyone. Thanks for being here so early on a Sunday morning. My name is Laura, I work at Collabora, and today I'd like to share with you a war story about how we built and grew our laboratory for upstream testing. I'm going to share with you a little bit about our infrastructure, as well as some of the challenges that we have to face while scaling up. So our main goal was to build a big test bed for open source projects to use. So of course we're going to need a diverse ecosystem of devices, so many different devices of different architectures and from different vendors. Of course we're going to need a software to automate the tests on the actual devices. We need a monitoring system, so a way to monitor and assess the health of the devices that we have in the lab. And we also need some recovery strategies. So mainly when devices starts to misbehave or don't behave as expected, we need some way of recovering them automatically or putting them offline automatically if they're not reliable to run tests. So it all starts with a commit. The developer pushes the changes into a development branch. The artifacts for the tests are built automatically. A test job is submitted and run. The results are gathered and parsed, and finally a report is generated and sent back to the developer. So from the lab perspective, we're interested in the part that runs the test jobs and makes the results available. What we chose for our lab is Lava. As we saw earlier, this is the linear automation and validation architecture. So it automates the boot and deploy phases of the operating system on the device. It has a really scalable scheduler. It allows to run thousands of jobs on hundreds of devices on a single instance. So that's really convenient for big labs. It handles the power on the devices, so it switches the power on and off on the devices when needed, and it also helps monitoring the serial output. And finally, it also makes the results of the tests available in many different formats, which is, again, pretty convenient. Lava, again, just takes care of this part of the CI loop, while all the other phases needs to be implemented with different tools. So in order to run devices in Lava, we need to fulfill a set of base requirements. Of course, we're going to need to be able to turn on and off the power on the devices remotely. We need access to a reliable serial console remotely. And finally, we need some way of booting an arbitrary combination of kernel, device tree, and rootfs remotely. For all the devices that we have in the lab, we rely on TFTP. So we need network connectivity at the bootloader level. And that means that we often have to build our custom bootloaders and enable all the features that we need for debugging. So there are a few steps to prepare the devices before they enter the lab. As far as the configuration of the devices itself in Lava, we have a couple of, you only need to define some Jinja 2 and YAML templates. So the device type template basically defines the characteristic of the device type. So for example, which kind of bootloader run on a certain device, which kind of command line options are needed for booting. Well, the device dictionary defines device specific characteristics. So for example, what command do we need to run to turn on and off the power or to access the serial console? And finally, we have the health check, which is a special kind of job associated to each device type. And the aim of the health check is to assess the health of the health status of each device. It's supposed to be run on a fairly regular basis. We run a health check on every device that we have in the lab every day. And examples of tests that you can fit in a health check are, for example, a battery test, or you can check the temperature on the device to make sure it's not overheating. You can check the network connectivity, basically all the tests that you need to make sure that the device is functional, you can fit them in health check. And whenever a device fails its health check, Lava automatically puts it offline. So it's really useful just to shut down all the devices that are not reliable at the moment. So Collabora maintains a laboratory running Lava, and we have, as of a couple of days ago, 217 devices of 38 different types, spread across 16 racks. Each rack is controlled by its own server, and that's also where the Lava dispatcher runs. And of course, besides all the devices, we also have a bunch of hardware equipment that we need to automate the boot and test phases on our devices. And this is what the device distribution looked like in January. So the vast majority of our devices are x86, 64, and ARM64 platforms. And we also have some QEMU instances that are mainly used by KernelCI. And the very vast majority of our devices are actually Chromebook laptops, but we also have some embedded SPC devices as well. So what kind of hardware do we have in the lab? So different devices has usually different requirements. So for embedded SPCs, what we use to control the power on them remotely are Ethernet control relays and PDUs. I left there some examples of the actual models that we currently have in the lab. Chromebooks are kind of a different beast. They have their own hardware debug interface, which is the Servo V4 and the SUSE cables. So Servo V4 allows you to control the power on the device, to access the serial consoles on the device, and also provides network connectivity through an Ethernet port. So you can fit everything you need to automate the boot and test phases on a Chromebook can fit inside just one hardware box. As an alternative, you also have SUSE cables, which pretty much have the same functionality, except for the network connectivity that you have to provide through usually through a USB to Ethernet adapter. We have a couple of servers as well in the lab, and for those we use the IPMI standard protocol just to control the power and access the serial consoles. And for all the devices, of course, we're going to need a bunch of USB cables with their fragilities. And also we use USB hubs. We find especially useful the switchable hubs, such as the YCush, especially for those devices that are controlled by just one USB connection, such as the Chromebooks. So that's really convenient, just not to having to manually intervene every time you need to replug the USB connection. As for the software, I left here a couple of links. You want to check them out. We use PDU daemon to execute commands on the PDUs. We use conserver to access the serial consoles and monitor the output. And the HDC tools are just for the Chromebooks. These are the software tools that allows you to interact with the Servo V4 and with the SUSE cable as well, just to control the power and the serial on the Chromebooks. For the interaction with Lava, we use Lava CLI. It's a command line interface, and that's useful to run the tests on the device and also configure and push the templates. Finally, we also have a Lava GitLab runner that serves as a bridge between GitLab and Lava. And yeah, that's pretty much it for the software side. So in our lab, we have two major users. One is KernelCI, which is focused on continuous testing of the Linux kernel. It's not only boot tests. We have a bunch of other test suites running on them. And the type of testing that KernelCI does is post-merge. So changes are tested after they landed on a set of monitor trees. So after the tests have run, KernelCI will generate some build reports as well as some regression reports for every regression that is found. The other major player in our lab is MesaCI, so that's the CI for Mesa 3D, and it does conformance testing and also performance tracking. There are a bunch of test suites that are currently run by MesaCI. I left a list here. A bunch of APIs and drivers are tested. And while KernelCI only does post-merge testing, MesaCI also does pre-merge conformance tests. So that's a little bit of both. And in this diagram, you can see what's the usage of KernelCI and MesaCI in our laboratory. As you can see, both projects keep our lab pretty busy. KernelCI uses almost all the architectures that we have in the lab, while MesaCI is focused more on x86, 64, and ARM64. And with so many jobs running every day in our lab, of course, the impact of any error or unreliability in the infrastructure can be quite big. So for pre-merge tests, you have the merge requests from users can get blocked, and definitely if a certain device type is not available. And also, there's a risk of merge requests getting rejected if there are many errors in the lab. So what we need to make sure from the lab perspective is that the merge requests from users do get rejected only because the changes introduced made the test fail and not because of any infrastructure error. Well, for post-merge tests, we have a risk of reporting false regressions. In this case, we want to make sure again that the infrastructure errors are reported as such by LAVA. And LAVA defines different types of exceptions that you can raise based on the type of error that occurs. We need just to make sure that the devices and LAVA itself is configured properly to do so. This is just a minimal list of the common issues that we have seen over the years. Of course, there can be hardware degradation. You can have faulty cables at any time, or batteries just failing, power chargers not working properly. All kind of network issues can happen at any time, and they can have quite a big impact. We also saw some issues related to the rack setup. So, for example, we had some laptops where the lid was slightly too closed because of how it was set up in the rack, and it was causing the device to enter suspend unexpectedly. So we have all kind of different errors that can happen. Of course, we can have firmware bugs either in the firmware running on the actual devices, or also firmware running in the hardware debug interface. So that's a lot of errors that can happen. I gather a few of my favorite pitfalls. These are issues, tricky ones that we have found recently, and we're still dealing with some of those. So one of the things that we saw is that sometimes it happens that the serial console will just stop outputting anything on the serial console. And if this happens during the test phase, it's kind of hard to understand in an automated way whether the kernel is hanging or whether your USB cable connection has dropped, or if it's just like an unreliable serial connection. So that's usually a tricky one to deal with. Another serial-related one is caused by interference. So not all devices can have multiple UART connections for debug. Most of our devices in the lab don't. So we have to share the same serial connection between the kernel and the test shell. And this sometimes can cause some interference, and of course it will confuse LAVA about the outcome. One way that we are thinking of many solutions to deal with this kind of serial issue stuff, and one approach that we are looking into is actually using a Docker container. So running a Docker container, connecting to the device over SSH, and run the tests on the SSH console. This way we can probably work around some of these serial issues. So as I said, there are also network connectivity issues from time to time, and if the network drops during the bootloader phase, that's usually something we can easily catch because Lava, of course, monitors the serial output. And if our bootloader is nice enough to print error messages, we can just catch the right patterns at the right time and just raise an infrastructure error. So that won't initiate like the outcome of the test. When this happens, we can also configure Lava to retry the job if needed. So when this happens, it's useful to catch error patterns. If network decides to drop during the test phase, that's usually worse, especially for devices that rely on a network-based system. So it's usually pretty hard to recover from these. We have seen occasional USB disconnection for whatever reason. And yeah, it's hard to recover from these kind of issues usually. So these are some of the best practices we came upon while working on these issues. So the first one is about writing robust health checks. So as I said, devices will be put offline by Lava if the health check fails. So we need to make sure that the health checks catch as many issues as possible automatically. We found very useful to monitor the Lava infrastructure error exceptions, and this is mainly to catch issues with specific racks or specific device types. We usually try to monitor also the device's health and the job queue as well. And this is to make sure that we have enough devices of a certain device type to feed all the pipelines for the projects. And and also to minimize, like, if a certain device type goes offline, and if we have redundancy, we're able to kind of recover from that. And last but not least, as I said, one best practice is to try and isolate the test shell output and kernel messages whenever possible. If not, we're trying to work around some of these issues. So next steps for our lab is, of course, increase the lab capacity and try to cover even more platform and different vendors as soon as they come out. While doing this, we are continuing to improve our infrastructure and our monitoring tools. I haven't included in this presentation how we actually monitor things, but yeah, Lava does have some APIs that you can use to monitor the status of each device and also of the server. And yeah, of course, while keep adding new lab devices, we also want to increase the coverage of test suites. So we're working on adding even more test suites on KernelCI and MesaCI as well. And that's it. If you have any questions, I think I have time, right? Very often, I'd say.
Can you give me a specific metric?
I don't have data at hand with the actual failures, but yeah, it happens pretty often. I mean, we have so many jobs running every day, and we rely heavily on USB, which is kind of not great. Like it breaks pretty often. I'd say the most common issues that we have is usually due to the serial consoles being not too reliable. The vast majority of devices that we have are Chromebooks, and we're using like these hardware debug interfaces that were meant for debugging. So sometimes like the serial connection is not great, and that causes all kinds of issues. So we try at least to retry the jobs when possible and catch the infrastructure errors as they come out. So I'd say we don't have to manually intervene every day. I'd go like every couple of days we need to maybe replug some of the devices because we, as I said, we use the switchable hubs to try and avoid having to reset the connection manually, but we don't have this set up on each and every device that we have. We're working on it, but yeah. I'd say like at least a couple of times a week. I haven't like really checked the frequency of it, but yeah. Of course, there's people in the lab actually taking care of all the devices.
I think you have lots of various tests, so how do you keep structure in your test sets?
So from the lab perspective, we don't really care about the test suites running. It's more the responsibility of KernelCI and MesaCI. You can check out the links that I left. Like everything is of course open source, so you can check out all the test suites and how they work. Yeah, some tests you just need a RAM disk. Some other tests rely, the most heavier ones, rely on network file system. Yeah.
Why is it that you have a lot more real devices than virtual ones compared to what Remy showed before?
I mean, it depends on the type of tests that you need to run. We use a lot of Chromebooks because we need Chromebooks. So, yeah, you cannot really emulate one. Yeah.
Do we have other questions? Because we have a few more minutes. I'll give you stickers. All right, no more questions, well, thank you.
Thank you.